So hello everyone and welcome to this Saphir webinar of August. Today we have the pleasure to introduce Dr. Attila Krasznahorkay from the ATOMKI Institute of Nuclear Science in Debrecen, Hungary. Attila is an experimental nuclear physicist and he has been working at ATOMKI since the 80s and his discoveries, latest discoveries, has been attracted, taken attention of the whole community, especially for these anomalous signals at around 17 mega electron volts, called the X17 particle. So please welcome to Attila to this Saphir webinar. Attila, please.
Okay, can you hear me?
Yes.
Yes, we can hear you.
Thank you very much for the nice introduction. It is a great pleasure also for me to speak about our recent results and give an overview of the experimental results about X17 particle. At your famous Saphir webinar, after the theoretical talk of Enrico Nardi. As you mentioned, I am working for the Institute for Nuclear Research in Debrecen, Hungary. You can see a picture. You can see a picture of the front buildings in the downtown of Debrecen, about our institute. Debrecen is the second largest town in Hungary, and it is completely flat. In contrast to your beautiful mountains, countryside. We have a close contact with the University of Debrecen and also with CERN. My son is working for CERN, actually. So let me tell you my leitmotif first. Since Galileo, we have known that one of the most effective ways to learn about the world around us is to conduct experiments. If we don't know something, let's ask nature itself. That's what experiments are for. I am going to speak about different kinds of experiments. In red, I show the experiments which are finished already and give results. In green, I will speak, you show an experiment which will give results very soon. They did the experiment and going to publish it soon. Then there are experiments which are finished already, but did not see the X17, just gave some constraints on the coupling constant and things like that. And then comes many experiments which have already the setup ready, even tested, but did not publish any results yet. It's not an easy experiment, it turned out. And there are experiments which are only just projects at this moment. They are not approved. So the first results we published was this observation of anomalous internal pair creation in beryllium-8, a possible indication of a light neutral boson. It was published in 2016. And then it gave a boom in the media because the ATOMKI anomaly signals for a new 17 MeV boson, which might be a gauge boson for a fifth force, as we learn from theorists. So we had a lot of citations already, more than 500, and it was published also in the media, in the CERN Courier a few times, and also in different other media. Before going to the details, let me show you the idea, what we did. So we used lithium-7 proton radiative capture and produced beryllium-8. You can see the excitation function of this reaction here. I can show you this very sharp peak at 441 kV, which excites very selectively this 17.6 MeV state. So that was the idea of the experiment, to use a very selective nuclear reaction which excites only one level. Because in this region, there are many levels actually in beryllium-8. But this reaction is very selective. And there is another resonance at higher energy, around 1 MeV, you can see here, which excites another level at 18.2 MeV, very close to the previous one. And it has also 1+ spin and parity. And such state decays to the ground state and to the first excited state. The first excited state is very broad because it splits to 2 alpha particles very fast. The 17.6 MeV state decays also to the ground state and to the first excited state. So let me emphasize this, the very selective nature of this reaction. We don't have background. I mean, in the excitation function, you can see some background. It comes from direct proton capture, and it has a multipolarity of electric dipole. It gives some mixture to these transitions. Such transitions are magnetic dipoles, of course, going to the ground state and the first excited state. If we are investigating such a high energy transitions, it is well known for a long time that it can decay also by internal pair creation with electron-positron pairs. The angular correlation of the electron-positron pairs are well known for a long time, can be calculated for different multipolarity transitions. In our case, we were interested in this magnetic dipole transition. And the angular correlation is smooth and gradually decreasing. But if you assume that a particle is created instead of the internal pair creation and the gamma decay, and then decays into electron-positron pairs, we can simulate the kinematics of this decay. It is a very simple two-body decay process. You can see the result of the simulation, which I performed for a transition energy of 18 MeV, and assumed the mass of the particle 10 MeV over c squared, 12, 14, 16, and 17. And you can see that in all cases, it shows a very well-defined peak, according just to kinematics. So what we can do, we are searching for a peak on a smooth curve. That's the signature that we create in a particle. The problem is that it is a very rare process. In this proton capture, the probability of creating a gamma transition is in the 10 to minus 5. The internal pair creation in the 10 to minus 6, and creating a dark photon, what we were searching for, is already in the 10 to minus 10 range. So we had to construct a very good spectrometer with very high efficiency to observe this transition. And we chose the very cost-effective solution for this. You can see a CAD diagram of our spectrometer. The particle beam, the proton beams, comes perpendicular to the screen, and you can see our target here at the middle of a carbon fiber beam pipe, a very thin wall beam pipe. The electrons and positrons can go through it. And then we used multi-wire proportional chambers. You can see them here with delay line readout for the simplicity to measure the X and Y position of the tracks. Then we used a very thin plastic scintillator to reduce the effect of the gamma rays, and a big scintillator to measure the energy of the electrons and positrons, to slow down them inside the detector. For the first time, we used 5 of these telescopes, and you can see also a photograph of them. They are the telescopes. The beam comes this way, and they are the telescopes perpendicular to the beam. You can see our gas system here, the electronics, and the data acquisition system. It was really a very cost-effective way of doing that. And let me show you the results. You can see here the energy sum spectrum of the electrons and positrons, which shows a peak at 17.6 MeV. The scale is normalized to the transition effect, taking into account the energy loss of the particles and so on. So if we use this lower resonance at 441 kV, we could observe this spectrum. You can see the 17.6 MeV transition, and the next transition is going to the first excited state, which was very broad. And then an oxygen transition. We used lithium fluoride target. And on fluorine, we have another reaction, a P-alpha reaction, and the final state is oxygen 60. And the first excited state in oxygen 16 is 0+. And we can see this 0+0+ transition here, which is very strong. And then we set gates on this full energy peak and transition to the first excited state. You can see the results for the angular correlation here for both transitions in circle and in black dots, and also the results of our simulations for magnetic dipole transition and electric dipole transition. In order to fit the experimental results, we mixed some electric dipole transition to the magnetic dipole to fit the data. And in this way, we could describe the data very precisely. Then we went up to the 1 MeV resonance and excited the other state, the 18 MeV state. And you can see we observed an anomaly around 140 degrees. You can see also some other transition going to the first excited state. It did not show any peak. And there is also a transition coming from aluminum, from the backing of the target. And it was used to check our spectrometer also. They did not show any deviation from the theoretical curve. But this 18 MeV did. And then, it was, the proton energy was exactly the same like the resonance energy. But we used a relatively thick target. So then we increased the energy somewhat, and this anomaly increased. So it was not an experimental effect, but it was something real. And that we analyzed it. We did a lot of simulations by assuming different energies for this X17 particle. You can see the results here for 16, 1 MeV lower and 1 MeV higher, and they really differ. And if we assume this energy 16.6 MeV, we could describe this anomaly very precisely. Let me tell you that we did the analysis for the special case for the asymmetry of the energies. So energy difference over the energy sum was in between 0.5, minus 0.5 and 0.5. So they were symmetrical energy distributions for this case. But we did it for asymmetric distributions also. You can see the results below. And it did not show any anomaly. If we did the calculations for the decay of the boson, we got agreement also with this. Then we calculated also the invariant mass for the particle physicist and got also a bump in the distribution. We were very lucky after that. At the same year, a new accelerator was installed in our lab. A new tandetron accelerator, you can see it here, and an analyzing magnet and switching magnet and many different beam channels. And we got also a beamline. And you can see here our very recent spectrometer, our latest, most sophisticated spectrometer. What we did at the tandetron accelerator, we used this previous version of the spectrometer, but in this case, we already used double-sided silicon detectors to track the electrons and positrons. They were more reliable compared to the gas detectors. And okay, first of all, we remeasured the anomaly for beryllium and got agreement. We were very happy about that. And then we measured also transitions in helium-4. You can see the anomalies also in that case, and more recently for carbon-12. Carbon-12 is a different case. It's 1 minus state decays to electric dipole. And in spite of that, we observed an anomaly. In such 3 cases, the excitation energy were very different. And this slide shows as a function of the energy of the X17 particle, the angle of the anomaly. As we expected from this two-body decay, larger the excitation energy, larger the transition energy, and larger the energy of the X17 particle, smaller the angle between the electron-positron pairs. In black, you can see the results of our simulations for 18, 17, and 16. And we could get nice agreement with the assumption of 17. This gives actually a kinematical evidence for the existence of this particle. Oh, I have to speed up. I'm sorry. The next experiment we performed in Vietnam. I mean, we had them to build a setup, and then they did the experiment for 1 month, repeated our experiment on beryllium-8. They were using only 2 telescopes, and they were set at 140 degrees to study such anomaly only. You can see the setup here, the DSSD detectors, the plastic scintillators, and the connected electronics. And also their accelerator, data acquisition system, and so on. Let me show you their results only. So they repeated the experiment at 1441 keV and got nice agreement also with the simulation. They went up to the 1 MeV resonance as well. And as you can see, the experimental results in black, they observed also an anomaly around 135 degrees. And when they assumed the decay of the boson, they could explain it. They could describe it. And in this way, okay, we got agreement with the results. And there is another confirmation of this X17 particle, which came from a Dubna experiment. It is a completely different experiment. They used a few GeV protons and deuterons and bombarded carbon, copper, and other targets, and detected gamma rays. Actually, 2 gamma rays in coincidence. And let me show you their experimental setup. So they were using lead glass Cherenkov counters, two bunches at some angle very far from the target, and they were even used plastic scintillators before then to identify if they were gamma rays or electrons. They published already their results. Let me show you their results. First, they investigated a particle around 1738. That was the reason they used these two sets of scintillators at some angle. But then when they noticed that we observed a particle at 17, they used only one telescope, and inside the telescope, they required coincidences between the scintillators. And in this way, they could study smaller masses. And they could observe this X17 with reasonably high confidence at the different reactions. You can see the reactions and NADC. And in all cases, they observed this X17 particle. This is the invariant mass on the horizontal. But it was a 2 gamma decay of this X17 particle. Then I asked them to switch on the plastic scintillator and identify the electrons and positrons. And in this case, they also observed this X17 particle, and they could confirm our results on the decay, electron-positron decay of X17. The next experiment, which is just running, is already a particle physics experiment at the Porsche Institute in Switzerland. They have already a nice superconducting solenoid spectrometer with a TPC inside. You can see the size, it's more than 2 meters long and 1 meter, more than 1 meter of the diameter. They developed this spectrometer to use muon beam on some target and study positron gamma decay, muon electron gamma. That means the abbreviation. But a few years ago, they started to use this spectrometer together with a small Van de Graaff accelerator to study the beryllium-8 with the same reaction. And in the solenoid, they detected positrons and electrons in coincidence. They gave a talk last month in July, actually, at the High Energy Particle Physics Conference. And they were speaking about run in 2012 and the physics run in last year. They did reasonably long, 1 week, 4-week long experiment and detected a lot of events. So it was a reasonable experiment, but they used a very thick target, actually, with lithium, 7 micrometer thick target. And in this way, they investigated both resonances at the same time. And let me show you the results. their previous results on the sidebands. They are also angular correlations, what you can see. These ones are coming from the lowest resonance, and they could describe the angular correlation precisely. And these ones are coming from the higher resonance, but the region of the signal is missing. The sidebands, they could describe reasonably well, but the statistics was not good enough to decide if they could see a peak, an anomaly or not. That's the reason they are planning to repeat the experiment at the beginning of next year. And they will publish the results after. At CERN, they perform many other experiments to study dark matter and also the X17 particle. They use a very special setup at the SPS, the proton supersynchrotron. You can see their setup here, which they were used also for surging the X17 part. So they used high energy protons to create positrons. And they use such positrons to scatter on the ECAL detector, which is plastic scintillator and tungsten combination. So in this way, they wanted to create the X17 here in the dark. And they are using a veto detector or plastic scintillator to avoid the charged particles. And then the X17 or Axion can go this HCAL1 scintillator, and then they may decay by 2 gamma rays or electron positrons and detect it in this scintillator. So they did not actually distinguish between the gamma rays and electron positron pairs, just measure their sum energy. And in this way, they could set some region for the coupling of X17 particle to electrons. So they could not detect the X17. There is another experiment. It was running at the beginning of this year, and they wanted to study X17 by using positron-electron collision. So they were searching for the resonance in electron-positron decay. In a similar way, they studied earlier the psi part. They used the PADME setup, which was constructed for positron dark matter experiments. They switched on the magnets, and for this electron-positron collision, they used just BGO scintillators, which could detect both gamma rays or electron-positron pairs, and the plastic scintillators before that. So they used high energy positrons and shooted them on fixed target. but it is a very inefficient way of getting new particles. So they had to use relatively high energy positrons. This slide shows an excitation function between 260 and 300 MeV. It is a simulated plot. So they measured the cross-section as a function of the energy of the positrons and expected this X17 peak somewhere here, according to our results. But unfortunately, this Baba scattering gave a very high background. So actually, the real peak to background was only a few percent, 2–3%. And even for a 1 month run, they could not collect enough statistics to see any peak in the excitation function. They are still analyzing the data. They are preliminary results, but it seems that such Baba scattering is really an enemy of this experiment. Let me speak about another experiment which started at CERN, a phaser experiment, which is really a particle physics experiment. And they want to measure dark matter particles or X17 particles and these kind of things very far from the collision points. So at CERN, all the big detectors are put to 90 degrees to the beam axis. But in this way, they say if they want to study light particles, they should go at very small angles to the beam. And that's the reason they went 48 meters from the Atlas collision axis and using a very small angle. It is an approved experiment. It is running already. So the idea is that if an electron-positron pair is created here in the scintillator from the decay of a particle, of an unknown particle, they were using magnets to bend such particles and measure their X and Y coordinates to identify such electron-positron pair decay. They are actually very far from the collision points. And in this way, they need to have some longer lifetime of the particle which decays here. And in this way, they could not observe the decay of X17 up till now. There is a very recent results from CERN also, from the NA62 collaboration. They studied the decay of K+ mesons to pion and 4 electrons final state. They could calculate it also from the standard model by assuming the QCD creation of a QCD axion, and they got a lower bounds of larger than 2 times 10 to minus 8. So that was the prediction. And they could determine upper limits, which was 1 times 10 to minus 9. And in this way, they could rule out the QCD axiom. And then other results from China, a big collaboration. They studied the decay of the eta prime particle to 2 pion and 2 leptons, electron positrons or muon decays. And they observed already some deviation, but it was too small. You can see it here from this light brown was the prediction without assuming any particles. And okay, they deviated a little bit from the experimental data, and they assumed a particle with about 15 MeV to describe the experimental data. In China, they are planning a super eta factory accelerator complex also to study further this process. And okay, I mentioned already Garnier, France. They constructed a few years ago a new jetty project with Bayam Bastin is leading the project, and they have more than 50 participants. And they plan to develop a long-range TAM research program in the MEV Terra Incognita energy range at the Spiral 2 facility. What they used actually 2 telescopes, very similar to our ones, using double-sided silicon chip detectors like we used, and plastic scintillators. Oops. Okay. Their idea was to set all of them into a large vacuum chamber to avoid energy loss of the carbon fiber beam pipe. And they hope that the background will be smaller. They did some experiments already. They got nice agreement for the 17.6 MeV transition, but they need more statistics. They want to have also a new experiment next year to get enough statistics to decide if they see the X17 or not. And another nuclear physics laboratory in Legnaro, we had a good contact also with this laboratory. This is a heavy ion lab, but they have also a small accelerator, this AN2000, which is a tandem, low energy tandem accelerator. And they started to develop also an electron positron spectrometer with the ideas of improved angular resolution by reducing the material budget. That means they put also the telescopes into vacuum. Improved angular coverage to measure out-of-plane correlation. You can see they want to put some telescopes in forward angle and also in backward. Oh, time is going too fast. It would be very important to decide if the emission of the particle was with L equals 1 or L equals 0 to determine the spin of the X17. That's the reason they are using more telescopes. They have simulated spectra already. That's our setup and our efficiency curve as a function of the angle. And this is their suggested setup with the efficiency curve. They were using different angles to have more smooth acceptance curve or efficiency curve. But they did not do yet any experiment. And let me show you just one more setup, which started to build in Montreal, Canada. They got the parts of the Daphne experiments from Shockley and Mines collaboration. They are plastic scintillators, and their idea is to have the largest efficiency for 4 pi, almost 4 pi solid angle for the detections of electrons and positrons. They are plastic scintillator rods, 1.4 meter long, and they are going to use multi-wire proportional chambers at the middle and want to get the highest efficiency for the spectrometer. You can see our spectrometer, the efficiency curve of our spectrometer, and here, and the efficiency of their spectrometer in Montreal. It is completely smooth, and if they see some anomaly, nobody would question it. There are many others in the world. Tibor Kibédi was my colleague earlier, 20 years ago in Hungary, and they started to construct also a spectrometer to study X17. It is a superconducting solenoid, and in this way you can see the path of the electron and positron in the solenoid. They want to build a TPC to follow the path, to track the path of the electron and positrons. And they are very optimistic, and they want to have an invariant mass distribution very good, and want to detect this anomaly with 50 sigma confidence. But okay, they started to build the spectrometer, but it will take time to finish it. Can I continue for a few more minutes, or I may stop it?
Yeah, please go ahead. Finish in a few
Thank you
minutes.
very
It's
much.
fine. Yes.
There is another spectrometer. They started to build in Prague. Actually, we are doing it in collaboration with our colleagues in Prague. We bought very strong permanent magnets. You can see them here. And with such a permanent magnet, we can create a toroidal magnetic field around the axis of the spectrum. You can see it here with the detectors. So they want to use a star detector here and TPCs in all the gaps, all the 6 gaps. The magnetic field is toroidal. It goes around. And in this way, they can detect also the paths of the electrons and positons. In Debrecen, we did not get enough support for that. So they are continuing building in Prague. They are going to use Time-Pix-3 detectors coming from CERN. They are very expensive detectors, but very high resolution detectors. And TPCs with GEM detectors. You can see the idea of the electron multiplication of the gas electron multiplier detector, and they got already some electronics also for it. You can see the status of building such detectors. And there are many others. I don't want to continue. The next one is a particle detector, and built by the Italians for the ENTOF collaboration. They are working at CERN for the ENTOF collaboration and can use their nuclear astrophysics lab, LUNA, to check the detectors. There are theorists also connected to the project, and detector research and development people. The idea to use neutrons to excite helium-4, but by using neutrons instead of the protons we did in Debrecen. But at the LUNA collaboration, they want to use also protons. They had different ideas for the detectors. They are going to use really particle physics detectors. You can see the sizes of the detectors here. They are really much bigger. And the specialty is the micro air well detector, which is a thin, relatively thin TPC, which is able to detect or track the electrons and positrons. They want to use a magnetic field around this to identify the electrons and positrons. They are just developing these detectors, and last month they tested it in Debrecen. That's the reason I wanted to show you. And okay, there are different other experiments, but if you have any questions, I can show you. Just one more slide about our plans. We are going to study the 2-gamma decay of the X17 particle. As we learned from the Dubna experiment, they observed 2-gamma decay. But then, is it a QAD meson, the X17 particle? There is a theorist, Wong, who suggests this. So they are suggesting that X17 is really a meson, a QAD meson, which is a very strange thing. So we are going to test this 2-gamma decay with very high efficiency and high resolution lanthan bromide. We did some experiments already, but the statistics was not good enough to see. Thank you very much for your kind attention. And excuse me about my long presentation, but there are really too many experiments running already to study this interesting particle.
Thank you so much, Attila. Indeed, it's quite impressive the amount of efforts from everybody in the communities to try to tackle this question of whether this particle exists or not. So we have time for a few questions. People from the audience for Attila, please raise your hands.
Yes, please.
I have a question.
Oh, okay.
I'm
Bastian,
sorry.
go
Okay.
ahead.
According to the data that you have collected all these years in the different experiments, can we say something about the couplings of this boson with the rest of the families of fermions, for instance, with quarks, the first family of quarks? Is it possible to infer something about that?
Yes. Actually, a theorist from the US, Jonathan Feng, they were using our branching ratio for this X17. So the branching ratio of X17 to gamma D. And they determined coupling constant to the different quarks, and also to the proton and neutron, and also to the electron. And they found that the coupling constant to the protons is much smaller compared to the coupling constant of the neutron. That's the reason they are thinking about the fifth explanation.
So in that sense, what they did is model independent, or?
Well, it is actually not. They assumed some model, but nobody else determined such coupling constant. The coupling constant to the electron is constrained by some NA experiments at CERN, but nobody was speaking about the coupling constant to quarks and protons. Only Feng.
Okay. Thank you.
The problem is that we are doing the experiments. Our detectors are perpendicular to the beam axis. So in this way, we cannot determine the angular distribution of the X17 particle. We cannot say if it was emitted with L equals 1 angular momentum or L equals 0, and cannot determine the spin of the X17. We may speculate, but it is not experimental data. That's the reason some experiments aims to have detectors at forward and backward direction also to determine such angular distribution. From the angular distribution, one could really determine the angular momentum.
Thank you.
So there are some efforts to know more about such particles.
Excellent. Any more questions?
Yes, some questions for you, Attila. It has been a lot of effort now to measure the X17 particle, and right now you have very nice results with 4 sigmas of 5 sigmas of significance. And in the future, you show us that will be some experiments with even 50 sigmas of significance with time predictor chambers. That's quite nice and unbelievable. How much time these experiments are running? I mean, the previous one, the first one that you did and you published in 2016, and the recent ones, and for instance, this experiment in Australia.
So the estimation performed in Australia, the simulation may be too optimistic, I would say. And the running time, we were usually using 1 week or 2 weeks beam time in Debrecen. And okay, in Vietnam, they were using 4 weeks because the efficiency of the 2 telescope setup was smaller. But in Frascati, in the electron-positron collision experiment, they were also using a month or 2 months. So in this scale. In Australia, that's a difficult question. It is a completely different experiment from the previous ones. So I believe they will have problems with the background, and in this way they cannot run with the same counting rate they are expecting, and should use also a few weeks of beam time to reach such very high resolution invariant mass.
Thank you, Attila. And just one more question. You show us a simulation of your angular efficiency. At Debrecen, you have this camel shape efficiency. And there was, I don't remember which of the future experiment you have this, probably in Australia, this U-turn shape. So how much affect this camel shape efficiency to your results?
Okay, very good question. Thank you very much. That's the reason we always tested our spectrometer with different transitions to see if we can reproduce the other transition without having any anomaly. So such experiments on the aluminum backing was running parallel, and also on the oxygen line was running parallel. And in this way, we were testing our efficiency during the experiment. In this way, we are sure that we are using the correct efficiency curve. And actually, we are determining such efficiency from the experimental data, from uncorrelated experimental data. We were calculating it also we're simulating it with Java code, and got reasonably good agreement with that.
Okay, thank you.
But it is nice if the efficiency curve is more smooth, especially in Vietnam. The efficiency curve was also very smooth, and no bumps and nothing, just very smooth. So in this way, this 2 detector setup is good, or maybe better than the 6 detector one. Smaller the efficiency, but more simple the acceptance or efficiency curve. In Ghana, they are going to use also 2 setups, so the efficiency curve will be smooth. So it's really a suspicious thing.
Okay, thank you, Attila.
Okay, if there are no more urgent questions, we thank Attila again for this comprehensive talk on experimental results for this X17 particle. Thank you so much for attending, and we will see you at the next webinar.